everyone. In this chapter, we'll be looking at antiderivatives. So in this slide, here we have the basic rules for finding antiderivatives. So basically, if you have a constant in front of the function f of x, you take that function before you take that constant before the antiderivative. And when you're adding functions, you simply add or subtract the antiderivatives as well. And when you have a function to the nth power, you make that x to the n plus 1 over n plus 1. And with our trig functions, with cosine, that becomes sine x as an antiderivative, and with cosecant, cotangent, that becomes negative cosecant, and e to the x power simply remains e to the x power, and 1 over x becomes the natural log of the absolute value of x. So here's an example of working backwards in antiderivatives. So this example is finding the function f of x when f prime of x equals x cubed root of x and f of 1 equals 2. So first we'll do a rewrite so that it's easier to solve, and we get f prime of x equals x to the first power times x to the 1/3. And then f prime of x equals x to the 1 plus 1/3 power, which becomes x to the 4/3 power, and then we use that to find the general antiderivative, which is f of x using the power rule, x to the 4/3 plus 1 over 4/3 plus 1, which simplifies to 3/7 x to the 7/3 plus c. And since we're finding it at f of 1, if we plug that in, we get the constant, which is f of x equals 3/7 x to the 7/3 plus 11/7. And that's our specific antiderivative. Here's another example by finding the second derivative. So in this example, we have to find f if f triple prime of x equals sine of x, f of 0 equals 1, and f prime of 0 equals 1, and f double prime of 0 equals 1. So first we find the antiderivative of f triple prime of x to get the the second derivative, which is simply negative cosine x plus c. Then we plug in that f double prime of 0 equals 1 at this spot to get the constant, which is 2. So that becomes f double prime of x equals negative cosine x plus 2. In the second step, we find the antiderivative of that, which becomes negative sine x plus 2x plus d. And when we plug in f prime of 0, which should equal 1, we get that d, the constant, equals 1. So that becomes f prime of x equals negative sine x plus 2x plus 1. And then for the final step, we find the antiderivative of that to get the function that we were looking for in the first place. So when we do that, we get f of x equals cosine x plus x squared plus x plus e, which becomes, when you plug in that f of 0 equals 1, that becomes e becomes 0, and then you're left with f of x equals cosine x plus x squared plus x. And that's the specific antiderivative. And another thing that you might be surprised by is that you can graph the antiderivative capital F of x from the function f of x. Even a cathedral of learning didn't know this fact. So in this example, the graph of a function is given. Make a rough sketch of the antiderivative f, given that f of 0 equals 2. So in the first step, we find the antiderivative, or we know that f of x is the antiderivative, so 0.02 would be f of 0, which equals 2. F is negative when capital F is decreasing, so that's from 0 to 1 and 3 to infinity. F is positive when f is increasing, which is from 1 to 3. And f of 1 equals f of 3, which is 0, and f of 1 is the minimum, while f of 3 is the maximum. And that's by the first derivative test. The antiderivative has a horizontal asymptote as and f double prime equals g prime, which is f prime of 4, which equals 0, and then f double prime of 2 equals the f double prime of 4, which equals 0. Then we test for which sign each point of inflection is, and we use all of that information to graph the antiderivative of f of x. We can also apply this to word problems with acceleration. So in this example, a car is traveling at 50 miles an hour when the brakes are fully applied, producing a constant deceleration of 22 feet per second squared. What is the distance covered by the car when it comes to a stop? So here we have our position s of t, which is an antiderivative of the velocity v of t, which is s prime of t, and then the antiderivative of that is acceleration, which is s double prime of t, which also equals v prime of t. So in the first step, we have that our acceleration function equals negative 22 feet per second squared. So our velocity function using the antiderivative would be negative 22 t plus c. And when we plug in the velocity as 0, we get we get 220 over 3 equals negative 22 times 0 plus c, and c equals 220 over 3, and then we're left with the velocity t equals negative 22t plus 220 over 3, and in the fourth step. So when a car stops, v of t equals 0. So 0 equals negative 22t plus 220 over 3, and it stops at t equals 18 over 3 seconds. So s of t equals negative 22t squared over 2, which equals negative 11t squared plus 220 over 3t plus d. So we know s of 0 equals 0 at its initial position. So when we plug that in to the previous function, we get that the constant d would equal 0. So s of t equals negative 11 t squared plus 220 over 3t, and the s final would equal s, like plugging in where it would stop from step 4, and we would get 122.2 feet. And then distance is just simply s final minus s initial, which is 122.25 feet. And that's how far the car travels. Thanks for watching.